Okay.
All right. Good afternoon, everybody. Welcome to lecture number 3. Welcome to people who aren't able to attend and instead will be viewing you remotely at some later time. I hope everybody's well today. I saw a number of course project information paragraphs were uploaded to the website, so that's great. I will start looking them over tonight. And from the sounds of it, from everybody who I've talked to so far, there's some really great ideas coming out, and I'm going to be really excited at the end of the term to actually see these things pan out and see the presentations on them. Do you have any particular questions that you have so far? Worth noting, the CESM project probably will be up by the end of the week if all goes well. So probably Friday I will aim to have the project description put up. It's going to be fairly simple. Basically, you're just going to have to compile CAM, Community Atmosphere Model on Yellowstone, and then use the model in order to run a simple dry dynamical simulation, and then analyze the results. So it should be fairly straightforward. It shouldn't take more than maybe a couple hours work, but we'll give you some familiarity with the CESM package and hopefully push things along. So picking up from last time then, so far we have derived the momentum equations in this form. In particular, we've shown that for a particular fluid parcel that we have floating around in space, I forgot my fluid parcel from last time, so instead I'm going to have a Kachiko thermos, which is actually full of fluid. It's my air parcel last time. We showed that if we have this air parcel floating around in space, that we have a bunch of forces that will be acting on the air parcel, causing it to accelerate. The forces that we've derived so far then consist of curvature associated with the fact that we're basically working in a spherical domain. We have pressure gradient forces, here expressed in spherical coordinates. Note that due to the presence of spherical coordinates, that's where we introduce these additional metric terms in the denominator in front of the pressure gradient. We have Coriolis forces, given by the sinusoidal Coriolis forces in the U momentum and V momentum equations. These are going to be the ones which are responsible for deflecting fluid parcels to the right in the northern hemisphere and deflecting them to the left in the southern hemisphere. We also have additional cosine Coriolis forces which allow linkage of the zonal momentum equation and the vertical momentum equation, which I did not discuss. And we have viscosity, which appears in each of the individual terms and it is represented by a Laplacian type forcing with viscosity coefficient nu out front here. This is generally very small in the free atmosphere and hence is typically neglected, as I'll discuss later. So I talked briefly about how we actually relate then the Lagrangian and the Eulerian frames, going back to the notion that in a typical global atmospheric model, we're not going to be dealing with fluid parcels that float around arbitrarily in space, but instead we'll be dealing with state variables which are located at explicit points along the globe. This is what is known as the Eulerian frame, since it's a non-moving frame, whereas the Lagrangian frame is associated with actual motion of the individual fluid parcels and their associated deformation. In practice, if we actually started with a grid like this in the Lagrangian frame and let our fluid parcels deform, it doesn't take very long, in fact on a period of hours of simulation time, before our fluid parcels become so deformed that it's very difficult to even isolate them in space anymore. Not to mention the fact that these are no longer even closely represented by four-sided polygons in space. So this becomes very complicated computationally, and consequently we're mainly interested in maintaining the Eulerian frame as our method of representing the computational domain. So, in order to relate the two frames, we derived a concept known as the material derivative. If we have a background wind field that looks like this, and we're interested in fluid motion through the wind field, we have our fluid parcel here floating around. We can take a Taylor series expansion of background space in each of the coordinate directions, including time, and we obtain that the change in temperature following a fluid parcel is then going to be equal to this expansion of partial derivatives times small adjustments in each of the coordinate directions. In particular, we're assuming that the adjustment is going to be very small, so we drop all higher order terms. So if we divide this expression through by delta time, then we obtain this expression right here. Note that the delta time then disappears from in front of this partial derivative of temperature with respect to time. And then we take the limit for small delta time, in which each of the coordinate directions then will also go to 0. And so they end up being Lagrangian derivatives following the fluid parcel. So here we have a Lagrangian derivative following the fluid parcel of temperature, Lagrangian derivative following the fluid partial of the x-coordinate, which is, what is that? U, yes, exactly the zonal velocity. The change in the x-coordinate following the fluid partial is exactly the zonal velocity. Same thing here, this is actually the meridional velocity, change in the y-coordinate following the fluid partial, and the vertical velocity change in the z-coordinate following the fluid partial. So consequently, substituting everything in, we obtain that the material derivative then takes this form, which allows us to relate the Lagrangian change of temperature following the fluid partial to its Eulerian counterparts, or in vector notation, we can write it in this form. So this is our relationship then between the Lagrangian frame and the Eulerian frame. So if we then turn our attention to the dynamic equations of motion that we derived previously, and insert the material derivative, we're going to obtain then an expression for the pointwise change, the Eulerian change, which is represented here by the partial derivative with respect to time, for each of the u, v, and w components at a certain fixed location in space. So then, with these four equations of motion, then we can obtain the Eulerian update of the velocity field at each point in space. Okay, but we're missing some equations in order to be able to actually simulate this on a computer. Namely, we don't know what the pressure field looks like. We don't know what the density field looks like. Whereas everything else is pretty much given. Everything else is expressed in terms of velocity components. So we need to come up with some mechanism in which we can represent both the pressure field and the density field. So the first one that we consider is the so-called continuity equation. So the continuity equation represents conservation of mass. So far, in this system, all we've really represented is the fact that acceleration is equal to force divided by mass. And I have not represented anything to do with conservation of mass so far. So the conservation equation that we can write down for this fluid parcel is essentially that the mass of the fluid parcel following the fluid parcel, so if I have a fluid parcel that's contained within a particular region, in this case a box, the mass within that won't change regardless of how I move it around in space. I'm still going to have the same amount of liquid inside here in case I accidentally press the button and everything pours out. But with that in mind, we obtain this as a starting point then for conservation of mass. The mass within any particular fluid parcel will not change in time. But mass is not a state variable. Our state variables are density, pressure, temperature, and each of the velocity components. Those are the quantities that we have stored at a particular location in space. So instead, we need to use the density in order to obtain the continuity equation. And this can be obtained simply by chain rule. So if we take the mass as rho times the velocity field, then we obtain that by chain rule, we apply the chain rule, to the expression for density, which is equal to mass divided by the velocity field. We can then expand it, and we get an expression which looks like this. So 1 over the volume times the change of mass with respect to time following the fluid parcel, minus mass divided by volume of the fluid parcel squared, times the change of the volume of the fluid parcel with respect to time. Okay? So this term here then, so in particular the first term, we know that it drops out by conservation of mass. The mass within the fluid parcel does not change with respect to time. And so we simply obtain this expression right here, namely that the change in density with respect to time following the fluid parcel is equal to negative density divided by the volume times the change in volume with respect to time. So the question is, what is it that actually causes a change in volume of the corresponding fluid parcel? Obviously, if I take the fluid parcel and just move it around in space, the volume of the fluid parcel is not changing. So you have to have some sort of special conditions in order to actually obtain deformation of the volume. So somebody have some idea then of what might be causing changes in the volume of the fluid parcel. What can we relate it to in terms of the state variables?
Temperature?
Temperature? Not necessarily, because we can still have a temperature change at a fixed volume. Compression and expansion. So if we take our fluid parcel then, and I work really, really, really hard, and I'm able to bend metal, this thing shrinks, parcel is going to change, and we get a compressive effect. So yes. And if we have expansion, then we can cause the fluid parcel to expand in space. And since we're dealing with compressible fluids, namely air, we're able to actually observe this. So compression and expansion. Here we have compression of the fluid parcel will cause a negative change in the volume of the fluid parcel. So the volume of the fluid parcel will shrink with respect to time. Expansion will cause the volume of the fluid parcel to expand with respect to time. And compression, we can relate that back to what we already know of the state variables, namely the velocity field, by saying, okay, compression is caused by convergence of the velocity field. If we have a bunch of velocity vectors all pointing into the same point, then that's basically compression of the fluid, right? Whereas if you have divergence of the velocity field, that is, all the velocity spreads out from a given point, then that's associated with expansion of the fluid parcel. So the basic idea then is that if we have divergence of the velocity field, our volume of the fluid parcel will increase with respect to time, and if we have compression, then the volume of the fluid parcel will shrink with respect to time. So the change of volume is then given by, using this hand-wavy argument, is given by the divergence of the underlying velocity field. And so consequently, this 1 over v times dv dt is actually given directly by the divergence of u. You can verify that the units are correct in this expression. The v's cancel out, and instead you have the 1 over time unit on the left-hand side, and on the right-hand side you have a spatial derivative of the velocity. So 1 over length times length over time, and you get 1 over time again. So substituting that in, then we get the Lagrangian form of the continuity equation, which represents the change in density following the fluid parcel as simply negative rho times divergence of u, and the Eulerian form, which can be obtained by applying the material derivative to the left-hand side and combining the two terms that pop out of that, we get an Eulerian form which looks like this. So just to verify that this is correct, if we have divergence of the velocity field, what does that correspond to? Expansion or compression? Expansion, correct. Divergence means div dot u is positive. Density is always positive, right? So what's the right-hand side going to be, positive or negative? Negative, yes. So if div dot u is positive, density is positive, and the right-hand side is going to be negative. Hence, the density will decrease with respect to time. And that's what you would expect. If you have a fluid parcel that expands while maintaining the same mass, then the density of the fluid parcel has to decrease in order to remain consistent. All right. So that gives us the continuity equation then that we're going to be using in Eulerian form. For tracer transport, it's pretty much the same idea. For passive tracer species, chemical species and moisture, which are transported with the flow, we know that the mixing ratio of the fluid is going to, or of the particular tracer species is going to remain constant within the fluid parcel. That is, if for every 10 million particles of dry fluid you have, so dry air within a fluid parcel, you have 10 tracer particles, then regardless of how you deform that particular fluid parcel, you're still going to have the same ratio of tracer particles to fluid particles. So how this is written then is simply that the Lagrangian derivative, so following a fluid parcel, of the mixing ratio Q for each species sub I is equal to 0 here. So following fluid parcel, the mixing ratio is constant. And this is simply the advection equation. So if we expand the advection equation then and multiply through by the density, notice nothing exciting has happened here. We just took the same thing from here, use the material derivative, and multiply through by the density. And we look at the continuity equation here on the left-hand side. This is the same thing from the previous slide, except expanded out in the Eulerian frame. We multiply this one through by qi, so nothing exciting, just all the terms now have a qi term in them. And we add both of those two terms together, and then apply reverse chain rule. You're going to observe that you get an expression of this form, namely the Eulerian time derivative of rho times qi plus the divergence of rho times qiu is equal to 0. So this is a so-called flux form expression for the tracer transport equation. So what would be the physical interpretation of rho times qi? So rho is a dry air density, or fluid parcel density. So what is rho times qi? Qi is a mixing ratio. So it's the number of tracer particles divided by the number of fluid particles. So rho times qi. Smiles. So it is actually the tracer mass density. So if rho is simply mass of the fluid divided by volume of the fluid, and the mixing ratio is mass of the tracer divided by mass of the fluid, then this is simply mass of the tracer divided by volume of the fluid. So it's a tracer mass density. So there's certain advantages to writing it in flux form over Lagrangian form. We're going to revisit both when we can go through the numerical methods in the next class. So the final equation, in order to draw everything together, we now have an equation for representing rho, one for representing the tracer mass, but the thing is we have not touched on anything for pressure yet. Now pressure can be obtained via the ideal gas law, which we've already imposed early on. We have P equals rho RT, remember. But we don't know temperature then, is that right? We don't have an evolution equation for temperature. So in order to obtain a closure equation then, for the equation that we've described so far, we're going to have to go back to thermodynamics and derive a corresponding equation. So recalling then the first law of thermodynamics, we have a change in internal energy, du, minus work done on the fluid parcel, which is equal to the diabatic heating applied to the fluid parcel. So if everything was adiabatic, namely if there was no external heating placed on the fluid parcel, then this dq would be equal to 0, and the change in internal energy would simply be given by the work done on the fluid parcel. So substituting in for known expressions relating the internal energy heating Q and work W to more relatable quantities. We have that the internal energy is simply equal to CV times dt, where CV is the specific heat capacity at constant volume. The work done on the fluid parcel is equal to P times d alpha, where alpha is 1 over the density, so it's known as the specific volume. And dq we're simply going to write down as J, and that's the external heating applied to the fluid parcel. So if we take this expression then, we'll perform these substitutions and then divide through by dt. Divide, in this case, again, hand wavy. We obtain that the change in temperature of the fluid parcel plus the work done on the fluid parcel is equal to heating and cooling. But this expression that we then derived, this contains all of the state variables, or this associates all the state variables that we know already and provides a corresponding closure. So the full set of equations then, taking into account the thermodynamic equations, the full set of equations then, the full primitive equations which describe fluid flow in the atmosphere then, are given by these three expressions for the evolution of the velocity field. The continuity equation, which describes conservation of mass. So whenever I talk about continuity equation, assume it's equivalent to conservation of mass. We have the thermodynamic equation here down at the bottom, which represents conservation of energy. In the case of J equals 0, so in the case of adiabatic flow, this represents exact conservation of energy. We have the ideal gas law, which allows us to relate the pressure, density, and temperature to one another. And we have an evolution equation for the mixing ratios. Okay. So this is the full set of dynamical equations that we need to solve in order to produce a dynamical core. This is the full basis for our dynamical core. Any dynamical core that is implemented will implement these equations in one form or another. Okay? Now this is an appropriate place to ask if you have any questions about the dynamics derivation that I've made so far. is that I'm very confused, I'll look it up later. Okay. I will continue then. So, as I mentioned, this is the full set of equations that we're aiming to solve. It's a lot of work to solve these for the atmosphere, and in particular, it's not really necessary. A lot of the terms in here are actually very small in the atmosphere, so it's wastes time computationally in order to really drag everything along, and also leads to possibly more inaccurate results. So the complete set of equations of motion, the primitive equations that I showed before, are typically too complicated to solve in practice, so we use a set of approximations to simplify the mathematics. So the simplest approximations include the shallow water equations, which are basically a one-layer fluid with no vertical velocity. You basically just assume that W is equal to 0 at the top of the fluid, W is equal to 0 at the bottom of the fluid, and assume that it has a uniform horizontal velocity associated with it. There's a Boostinesque approximation, which has to do with how you approximate the density field. But in general, these simply work in order to simplify the set of equations. But these are what we consider to be overly simplistic approximations. Shallow water and Boostinesque generally, they're really strong approximations in the sense that they really tear down the primitive equations to their simplest possible form and allow you to simply consider that aspect of the numerical methods, but it's not a particularly good model for representing the whole atmospheric system. In order to do long-range climate simulations, these two approximations are generally too simplistic. However, there are a number of approximations that we can use. First of all, the equations that I showed you earlier were the full set of Navier-Stokes equations associated with fluid motion. This first approximation that is done in almost every atmospheric model is the removal of the viscosity term. And that is simply done because typically the viscosity term has a scale of approximately 10 to the minus 15 in the free atmosphere, whereas the other terms are approximately 10 to the minus 2. So viscosity is more or less numerical error. It's basically numerical error on the scales that we're interested in the global atmosphere. And so we constantly drop the viscous dissipation in the free atmosphere. It does become relevant in the boundary layer near the surface, where we have a rapid change in the velocity field over a very short distance, associated with the fact that, as you see outside, there's a lot of friction going on the ground level, but only a short distance up in the atmosphere, it basically is allowed to flow freely. So in that very short distance, the velocity field will change very dramatically, and in that case, you need to take into account the viscosity. But in a free atmosphere, it can be ignored. So, turning back to the basic principles of the Earth's atmosphere, the radius of the Earth is very large compared to the total depth of the atmosphere. And consequently, it seems unreasonable to approximate the atmosphere as a full three-dimensional fluid. In fact, we can typically get away with approximating as nearly two-dimensional. So one thing that you can take into consideration about spherical geometry is the fact that if you have true spherical geometry with spherical coordinates, going from the middle of the sphere, which is located at where my two hands come together, if you expand outwards, the size of the elements will increase as you get farther away from the origin, right? So if you have a particular element patch on the sphere, and you take it out to be at some much greater radius, the element expands relative to, or proportional to, the radius of the sphere squared. But for our considerations, we're only considering a very, very tiny, tiny thin shell existing already at 6,400 kilometers away from the center of the sphere. So if we take into account the full divergence associated with the size of elements on the Earth, it's somewhat unnecessary. So consequently, the first approximation that is typically used in designing these atmospheric models that does more than simply remove the viscosity term is the so-called shallow atmosphere approximation. So this approximation closely approximates the atmosphere as a thin shell existing along a much larger spherical surface. Namely, the thickness of the shell in this case has to be much smaller than the radius of the Earth, so the vertical scale has to be much smaller than the horizontal scale. So this is one of the first that is used in any operational model. There's only a few models out there that have the option even of using a deep atmosphere approximation. But in operational mode, they will almost always run as a shallow atmosphere. And this dramatically simplifies things. As compared to the equations that we saw before, first of all these radius terms are replaced with radius of the earth terms. So all the r's are replaced with a's, which are fixed values. So they don't change vertically. Also, several of the curvature terms are dropped from the expression because they're assumed to be much smaller than the other terms when you actually expand it out in the shallow atmosphere. And the cosine Coriolis terms that I glossed over earlier are also dropped from that expression. The reason that I glossed over them earlier is because they're almost never used in practice. We only ever care about the horizontal Coriolis terms. And in addition, the viscosity associated with the vertical is also dropped if it was not already dropped. So shallow atmosphere approximation then is one of the first used. The Euler equation approximation is always used. And the final one I'm going to talk about is the hydrostatic approximation. If we turn our attention now to the vertical momentum equation that we described and write down the typical scales associated with each of the individual terms, we can write them out as approximations in terms of meters per second squared associated with each term. So we find that there's a dominant, the two terms that are dominant are the vertical pressure gradient term and the gravitational acceleration on the fluid parcel. And these are approximately equal with magnitude 10 meters per second squared. The next biggest term is the vertical cosine Coriolis term, which we've already dropped as part of the shallow atmosphere approximation. So the jump between here and here is about 4 orders of magnitude. Then the next term is this curvature term, which we dropped in the shallow atmosphere approximation. That's 2 more orders of magnitude smaller. And then finally, the vertical acceleration is about 8 orders of magnitude smaller than the hydrostatic balance term. So that means if we wanted to calculate the vertical acceleration on our fluid parcel, given all these other quantities, we're basically looking at 8 decimal places in the difference of these two terms in the hydrostatic expansion. So we're basically given this term is 9.8616 meters per second squared. This term is 9.8166, etc. So many on decimal places. Calculate this very, very tiny difference, and then that finally gives you the vertical acceleration. Consequently, this equation turns out to be absolutely terrible for approximating vertical acceleration. So you can understand why. If you're ever taking the difference between two numbers which are very, very close to one another, there's a lot of room for error. So in the hydrostatic approximation then, we simply say that, okay, this is not a good equation for approximating vertical acceleration. So consequently, we're going to drop this and simply write this as a balance term, a balance expression. We're interested only in balance between these two major terms right here. So with that in mind then, we turn back to the equations of motion and we say, okay, we're going to drop the acceleration, the vertical acceleration of this expression, and instead treat this as a constraint equation. Note that this is no longer a dynamic evolution equation here at the bottom because there's no time derivative associated with it. All it says is that whatever your state variables are at a given time, they need to satisfy this constraint right here. Okay. So that doesn't mean that there is zero vertical velocity in the system. It just means that the vertical velocity needs to be diagnosed or computed from the other state variables that we have in the system. And that's typically done from the continuity equation. And I'll discuss that next Monday, probably. All right. So that is everything then that I wanted to discuss for you deriving the equations of motion and their corresponding approximations that we use. Any questions? No? No questions? Good. All right. So we're going to go back to the numerical side of things now. Now we have our set of equations of motion which govern the associated dynamics of the system. So I'm going to talk to you briefly about an overview of the community Earth system model. So CESM is the recently renamed as a 2010 version of the community climate system model, CCSM. So have you ever hear anybody refer to CCSM? That was the progenitor to CESM. And the community climate system model was originally released in the form of the climate system model in 1996, and then adopted the community climate system model in 1998. Consequently, many of the resources which are available for CESM still maintain the CCSM model. So if you look at the code base, for instance, for CESM, it actually had just a CCSM all over it. So CESM was originally developed by the National Science Foundation and the Department of Energy. The model is freely available as an open source project, requiring only a simple registration process to download. It's maintained by the National Center for Atmospheric Research, based out of Boulder, Colorado, and they have a whole help and support team to do outreach to the scientific community. So the most recent version of CESM, however, does not compile using open source compilers, which is very disappointing for an open source project. That means you cannot simply download the CESM code, put it on your MacBook, and compile it successfully. It's very sad. They really need to fix that. For an open source project, you should run open source compilers and not force you to spend $600 on a provider to compile it. And that's the academic license cost. Anyway, so it requires a proprietor PGI or Intel compiler. The CESM is designed to simulate many components of the complete Earth system, ranging from incoming solar energy, stratus clouds, precipitation and evaporation, ocean, atmosphere, all types of clouds, ocean bottom topography, land surface topography, land processes, runoff, hydrology. All of this is included in one community Earth system model. There is also modules in order to do sociology if you're so interested. We can model land use changes over time as approximated by sociological or economic models. Components of this system have been written by pretty much almost every major university in the US and many of the ones from around the world in order to add additional features for particular studies. You can do carbon cycle, you can do polar sea ice. Generally, it's just a very general purpose model. In order to get it to do what you want, hence you need to do a little bit of work in order to actually kind of narrow down the options. The basic model is based in a spoke-like framework built around a central coupler module. So it couples together individual models which were developed for the four major processes. You have the atmospheric model, which is the community atmosphere model, CAM. You have the sea ice module, nicknamed Sea Ice. That's an awesome acronym. Ocean, which is run via the POP model, which is the Parallel Ocean Program. This acronym was actually created as a response to the GFDL MOM model. I'm not sure what the first name stands for, but the last are our ocean model. And then CLM, which is the community land model, that handles the land surface and land ice sheet. So these are all linked together via a coupler process. So the way that the coupler works is basically it's designed in order to communicate data effectively between each of these individual models, which are potentially found on different grids. So this will require conservative and accurate remapping of state variables between grids. If my land is emitting a certain amount of water vapor into the atmosphere as a consequence of evapotranspiration, you need to take into account the exact amount of water vapor mass that it's emitting and make sure that the atmosphere is also receiving that exact amount of mass and make sure that it's receiving it in the right location too. Now the difference being, the two grids might be completely different. You might have one grid which looks like a cube sphere grid, which is what the atmosphere model is running on. You might have an ocean grid which is running on this really cool tripolar grid. The reason that it's tripolar is it has one pole down in Antarctica and it has two poles here, one over Alaska and one in northern Europe. The reason that it does that is because having poles over the ocean in an ocean model tends to result in computational issues. So why not just move them over land where they no longer cause any problems? So that's the default for the Parallel Ocean Program model. All these are built around a central driver interface. So whenever you execute CESM, you actually execute the driver. The driver then sets up the coupler the atmosphere, sea ice, and land modules and ocean modules on individual processors. So the coupler will take up a certain chunk of your processors, the ocean will take up a certain chunk of your processors, and the atmosphere, sea ice, and land modules will be local on your processors. The reason that these two are right next to each other on the same set of processors is the fact that there's a very tight coupling between land processes and atmosphere processes, which requires a significant amount of communication. So we speed things up then by causing you not to have to make large communications across multiple processes.